just to check. Okay.
Okay. All right. Our final speaker for the workshop is Eluned Smith. So Eluned did her undergrad and PhD at Imperial College in London, and then she moved on to do her first postdoc in Germany, in Aachen, and after that she went to Zurich, and now you are at MIT. Yeah, that's your affiliation. Very good. Okay, so yeah, and we will hear about low latency machine learning at the LHCb experiment. Please go ahead.
Thank you very much. All right. Hi, everybody. Yeah, thanks for the introduction. So I am a faculty here down the road at MIT. And I will talk today a bit about a project that we started about 6 months ago, mainly with, this list of people here, which are mainly people in my group, but then also we have some collaborators at CERN. And as the title suggests, I'm going to be focusing, so it's a bit of a change from the last talk, a lot on how quickly we can run machine learning algorithms. So I wanted to firstly, because this is obviously a broad audience, just motivate a little bit why we care about having very low latency or quick inference within particle physics. So everything I'm going to be talking about is using data from the Large Hadron Collider. So this is this 27-kilometer ring that we have in Geneva. And how it works is essentially we have bunches of protons. We have about 10 to 11 protons in every bunch. And these bunches get collided every 25 nanoseconds. That then creates a lot of data which is collected by detectors. And crucially, because we do not have infinite amount of money, we cannot store all of this data, and that requires us to make very quick decisions on what type of data to save. And we call this formally real-time selection. In the jargon, we call it a trigger. If I ever say trigger, I just mean this real-time selection. Okay. So I will take 5 minutes just to say why we care about, so this whole talk is going to be about how we can increase the size of our data sets over the span of the next kind of 5 to 10 years. And I just want to motivate why we care about collecting as large data sets as possible at the LHC. So you can see what we do at the LHC is basically like a microscope on the universe. So we collect these protons, we make all this data, we collect it with these detectors. But crucially, the more data that we can collect, essentially the higher scales of energy that we can probe. So we know in our universe that there are many things that we can't explain, right? We don't know what dark matter is. We don't know why we have way more matter than antimatter. And because we haven't seen yet any fundamental forces that explain this, we assume there must be heavier, unknown particles out there that we just haven't yet seen. And so if we collect more and more data, essentially it means we can push the limits on the scale of new physics. Now, of course, in natural units, energy is just 1 over length. So you can also see this kind of like as a microscope. And so just to put this in context, I was going actually through this morning in terms of also when these things were discovered. So bacteria, which is about 10 to the minus 6, that was discovered in apparently the 1600s. And then like nanomaterials like graphene, that's 10 to the minus 9. That was kind of more started as a field in the 1950s. Again, kind of nuclear physics is around 10 to the minus 15, so that's the size of the proton. At the LHC right now, the types of scales that we probe is about 10 to the minus 19 meters, so that's where we are right now. And we're going to increase the luminosity over the next 5 to 10 years, and that's going to effectively increase the kind of scales that we can probe to something around 10 to the minus 21 if we can get these really big data sets. So that's why we want to be able to do this. Now, there are 4 different main detectors at the LHC, and some of you in IAIFI may be more familiar with CMS, which is the one here in the bottom left, who also have a lot of work going into this kind of fast, low inference machine learning. And I just want to highlight the particular difficulties to the LHCb detector in terms of our dataset challenges. So you have these 2 what we call general purpose detectors on the LHC, so CMS and ATLAS. And these are really designed to look directly for heavy particles, such as, for example, the Higgs boson. And there you have a paradigm where the production rates are fairly low. And also what you're looking for is very high energy compared to most of the collisions you produce. So you have a fairly low production rate, but also a very distinct signature. LHCb, on the other hand, it is a general purpose detector, kind of what we say in the forward region, but we have it in the forward region because we really want to look at something called a beauty quark or a B quark. And in contrast to other experiments on the ring, these are produced, like there's millions of these produced a second for us. We have much higher rates, but also they don't look that different from the other stuff that's produced in our detector. So essentially, they look a lot like our background. So this means that the type of scheme we have to have for this real-time selection at LHCb is very different from ATLAS and CMS. I kind of summarized this here on this slide. So on the left-hand side, you can just see the amount of bandwidth that detectors are going to be taking as a function of time. And so, yeah, here you see, down in the 1980s, we were really very, very small amount of bandwidth. And if we go up to about 2035, which is the detector that I'm talking about today, which would be LHCb upgrade 2, there we're going to have orders of around 200 terabits of data a second. And that's essentially the highest rate that anybody has to deal with in particle physics. The other problem, so that's the high rate, and this other problem is the fact, as I pointed out before, that we are not looking for like this kind of paradigm, which is often used of a needle in a haystack. If you have a very distinct thing that you're looking for, like with ATLAS and CMS, for us, we're really just trying to distinguish like one needle from a slightly different looking needle. And so this means we have to be very clever about what we do. So what we have currently running now at the LHC is we have the first, what we call software-only trigger. So because we really need the full detector information to be able to make a decision, because they're more complex decisions, we can't have an initial filtering process using local information. We have to read out the full detector, which is millions of channels, into software. So this at the moment corresponds to 40 terabits of data a second straight into software. And this was actually pioneered a lot by Mike Williams, sat in the front row. And we then use GPU architecture to have an initial kind of tracking selection and make kind of an initial reduction in the rate, and then we have some other calibration and alignment, and then we essentially, in the end, have reduced it to just about 40 gigabytes of second to disk. So this is what we currently have, and this is already very innovative because, as I say, it's the only place in the LHC where you have a software-only trigger. But in about 7-ish years' time, we're going to make it even harder for ourselves because we're going to increase what we call the instantaneous luminosity. So, sorry, I didn't explain this. So this is a very rough sketch, but basically you can choose, well, we choose with how much we essentially overlap our beams, how many inelastic collisions we have every bunch crossing of protons. So at the moment, we have around 6. We want to overlap them even more so that in around 7 years' time, we're going to have 40 inelastic collisions per bunch crossing. And that means that we're going to increase the amount of data that we collect. And it also gives us another problem because in order to be able to analyze this, we also need to save even more data. So we need to save a lot of timing information as well to be able to separate essentially each of these different vertices. So the corollary of this is we're going to have a much larger increase in rate. And it is not clear to us right now how we can go about to actually deal with this 200 terabits of data a second that we're going to have. So this is what we have in our initial layout for this upgraded detector. So you have here at the top left, essentially, the full raw rate. And then you're going to transmit. So you have to remember that these experiments are like 100 meters underground. And down underground, you have certain electronic boards, but all of the GPU farms, CPU farms sit above the surface. So initially you have this rate, and then we're going to have to transmit that from underground, above ground, to where the GPU farms are. And it's not clear at the moment really how much data we want to then transmit above ground. And at the moment, it really looks like to be able to do this, we're going to have to do a lot more compression actually underground on the electronics before sending that data up to the GPU farm. And this is not something we had to do at the moment. At the moment, it was possible to basically ship most of that data from underground to above ground, but with this increase in rate, it looks like the kind of most beneficial way of moving forward is to have some form of additional compression on the front end, or at least on the electronics underground. Okay, so yeah, essentially we want to look at whether or not we can compress on the electronics. So the project that we've been working on is looking at this kind of unique problem, and we've picked, so the LHCb detector is made up of many sub-detectors, and one of the detectors is called a calorimeter, which is a fairly data-heavy detector. So for the non-particle physicist, a calorimeter is essentially where you have a big, something with a really high Z, so like lead or whatever, and your particles going through it then interact through something called Bremsstrahlung, and then you have essentially a shower, and then you measure that shower. And because you have this multiplicative effect, they have a shower of particles, you have a lot of data. And so we, so you essentially see that here in green, and I also show like a sketch here. So on the right-hand, like this longitudinal example is kind of a shower progressing, and then you see like a 2D face-on image of that, of what it can look like for different levels of like what we call pile-up, so how many events you have in your detector. And these showers, the way we detect them is essentially your electrons are then detected by something called a photomultiplier, which basically, if you have a particle coming past, it creates the current in that device. Then when we have all of these individual channels, eventually what we want to do is then like group all of these channels together. This is a very crude sketch, but group these channels together. And then by summing up all the individual channels in a shower, we can then say, okay, this was the total energy of this incoming particle, and this is the total time of that incoming particle. Now, it's quite a lot of like detail, but this is kind of relevant for then what we try to do with this project. So these PMTs, these photomultiplier tubes, what they then receive is essentially an analog pulse. So as you have a particle coming through, it creates this current, and then you have a voltage like increase or decrease versus time. So this is what is read into these detectors. These then have to be processed on these front-end electronic boards, and the first thing that we do, we have something called ASICs. So these are hardwired circuits, essentially, which have very specific tasks, which are already kind of decided, where one of these is just going to do an analog integration to get the energy, and this other one called Spider is going to essentially, because this is an analog response, convert this to a digital output. This is called an ADC converter. And basically the summary of all of this is that this Spider chip here, it will then take this pulse and put it into 32, kind of represent it as 32 times 10-bit numbers. That is what is currently decided. This is already decided because the timeline for these ASICs is kind of a lot longer than the type of hardware I'm working with, so this is already set in stone. We have 32 times 10-bit numbers. Now, the issue is that we cannot transmit all of this data, essentially. 32 times 10-bit numbers, if you just do the maths, we have about 30,000 channels, and at the crossing rate that we will have, that's essentially just from this one detector, order of 100 terabits of data a second. That would already be the entire bandwidth that we have from one detector. So this is too large. And this essentially presents the problem that we have. We need to be able to compress this data down to something which is more manageable, and we have to really be able to do it on these front-end boards already before even going any further along the acquisition chain. It is important, however, that we can still preserve the information in this pulse shape, and the main thing we want to extract from this is the time of arrival. So here you see on the x-axis essentially like time in nanoseconds, and this shape can be used to give us kind of almost picosecond level timing, which is really important to correctly match our clusters to the right rest of the event to get the right reconstruction. But we also care about the actual shape of this pulse. So you can see the kind of different colored lines here, and these represent different longitudinal fluctuations in the showers that we also want to be able to record, and there's some other kind of intricacies there. So ideally, we would be able to record this whole pulsar shape, but as I say, we can't do it in the current form. So what we have looked at is essentially trying to use these field programmable gate arrays. So these are like configurable logic boards, unlike your ASICs. They already exist on this front-end board to do kind of already basic manipulations of some of this data, but we want to see if we can run machine learning compression algorithms on these FPGAs to be able to compress this down to a level that is then manageable. Now, the reason why this is particularly difficult and has not yet been done so far at the LHC, in this case, is because these are really sitting right on the detector, what we call front end. So here you have like a 2D cut through the LHCb detector, and this is the fluence, the kind of, if you like, the rate of radiation. In this case, it's hadrons that like these areas are going to be receiving. And very roughly, I sketch here this black box, which is where the front-end boards are going to be sitting, so where these FPGAs are going to be sitting. And they have a relatively high level of radiation, which causes problems, because if you have radiation, if you have a random particle coming through, it can just flip a bit, basically, and that then messes up your algorithms. So this is essentially the requirements that we therefore had for this ML model. It has to be able to compress this pulse shape by about an order of magnitude to be able to kind of get this off the board in time. That pulse shape should still, like the compressed version, should still contain the main information of that pulse shape. We have to run it on this front-end FPGA, which is very small, so we want a latency as small as possible, ideally around 25 nanoseconds, which is the crossing rate of the LHC. And another reason to be very small is that if you are very, very small, you can basically fit this model in the more radiation-hard part of the FPGA that I'll talk about shortly. Okay, so now a little bit more on the ML part. So what we did here, which is maybe kind of the obvious thing to do, is we used an autoencoder. So I assume most of you know what an autoencoder is, but essentially you take some input data, you compress it down to some latent space, you can then decode it, and your loss function is normally just the mean squared error between your input data and your reconstructed data, and you use that to then train the weights which map essentially going through each layer of the network. So this is what we used for this compression problem. So essentially, we're only using of course, we have to train with the encoder and the decoder, but we only care about actually compressing it and then passing on the latent space. So we trained this with simulation samples around 20,000 pulses. And so the first thing we did was to have the most naive. So we had this 32 input numbers. We want to get down to something like 2 ideally, because that's about an order of magnitude decrease, 4 or 2. So the first thing we did was ideally just half this each time, but then essentially have as a hyperparameter the number of floating point operations that each network took, because that's a very rough approximation for how long the latency is going to be to run this thing, so the inference. And essentially, this is a little bit of a rough and old plot now, I apologize, but so this is the number of floating flops here on the x-axis. And essentially, you can see that the really simplest possible model, so just going 32 straight down to 2, which has the least number of operations, performs as well as the rest of them. So essentially, this is what we went with. And then the other thing one needs to care about when you're looking at FPGAs is that you really care about not just your model structure, but you also care about the number of bits that is used to represent everything in your model. So the number of bits that is used to represent the weights in your model, and the number of bits that is used to represent the latent space in your model. And the reason for this is that we really care about every bit. So we have, ideally, you would have a smaller bit representation, a smaller bit width as possible for everything that you can compress into. So here what you see is essentially the MSE, so the size of the loss function, as a function of the bit width that we used for the latent space. And yeah, in this case, we picked 10 because that was deemed good enough while still being relatively small. So that is essentially the kind of initial model that we developed. So then the question is, does it do what we want it to do? So kind of by definition, if it's going from 32 to 2, still with 10-bit numbers, then that has already reduced it by the order of magnitude we need. But then the next question is whether or not it actually then allows you to extract the same information as on the original pulse shape. So this is just some rough kind of showing the validation of the pulses. So this is just kind of random samples that have been picked. So you see in blue, essentially, the original pulse shape in 32 times 10-bit numbers. And then in orange, you just have the reconstructed. And the main takeaway of this slide is just that, like, this looks fairly good. What we also want to care about, of course, is that you don't have, so we train this across a very wide energy of clusters. So you see kind of here in the legend, you see the number of, or the amount of energy of the original incoming particle in this case, that this pulse shape corresponds to, and you have a large range, therefore, of your pulse shapes, and you want to make sure that your MSE doesn't kind of have a worse performance, for example, for low energy pulse shapes, which would then be biasing, or the other way around. And there's not, so this kind of plot down here on the bottom right-hand side, this shows the, essentially the amplitude of the pulse shape, so the more negative, the larger the energy versus the MSE, and there's kind of, broadly not like a huge trend. Okay, so the next kind of obvious thing to do is just to check, okay, the physics information that you would typically then use to extract from these pulse shapes, is this then severely compromised by this compression that we've been forced to do? So these pulse shapes, as I say, is used to extract the time at which the particle arrived, and this is really important because for this experiment to work, we have to be able to get this down to kind of 0.1 of a nanosecond, roughly order of magnitude. And okay, this is with original more than 32 pulse shape, but this is just kind of to give you a visualization of what we do. So if this is the pulse shape, you use something called a continuous fraction discrimination algorithm that kind of just always takes the midpoint between the lowest and the highest point in the peak and just says that is the time of arrival. This is just how we choose to define time, if you like. And so we can run this type of algorithm on the original pulse shape and on the reconstructed pulse shape and just check that what we get in terms of our timing resolution isn't degraded from having done this compression. And so you see here on the right-hand side the kind of histogram over all of the testing sample. And actually, now, for technical reasons, I'm being a little bit unfair to the original pulse shape here, but if you take this at face value, you actually gain in precision when you do this reconstructed compression. And the reason for that in this case is because in the original pulse shape that we've used here, you actually can have quite a lot of noise, which degrades the quality of the algorithm. But if you then have this compression, it's basically a smoothing algorithm, so it can often actually lead to better extraction of your timestamp. There's a little bit of a caveat here in that this has got more numbers than the 32 that we were using for technical reasons, but the conclusion is more or less the same when you have 32 original numbers. So essentially, we can kind of show with this that after the compression, you can still do as well, if not better, than on your timing resolution for these particles. Okay. All right. So, okay. So the other thing that we, if we only wanted to take timing, then you could actually compress this to a latent space of 1 and just take out the timing information. But what we're specifically interested in is also preserving the shape of the pulse. And we want to then show that if we take this compressed representation of this pulse, it also then helps with the final energy reconstructed from your incoming particles. So just as a reminder, what we do here is you have an array of pulses, and those have to be clustered together, and then once you group them, you say, we sum up the energy, and we say that is the energy of that incoming particle by summing up all the channels in a certain shower. And what you see with this is fairly preliminary, but what you see here is essentially we've looked at doing this clustering after the compression with different options. So this first green line is if you say we're not going to use any timing information whatsoever. So you basically just have the energy from each cell, but you have nothing about the time of arrival. And you can still get, you can still make an estimate of what your energy would be, but it's worse than if you then add in timing information. Then with your orange kind of line here, you have essentially, we do a non-ML based extraction of the timestamps of the time of arrival. This blue line is then if you use an ML kind of approach the timestamp. But this pink line, which is essentially the work that we are doing, is if you now give these two numbers, and not just the timestamp, but essentially the entire latent space of the pulse shape, to your clustering algorithm. And here you can see there is quite a substantial gain in the resolution of the of your extracted energy. So the takeaway here is essentially like this compression. The fact that you can get the full pulse shape really does also help with the resulting physics in the end. Okay, so we kind of show that the compressed shape does its job and you don't lose information. So now this very last part is, okay, like this works, but does it work quickly enough? Because as I say, these are such small FPGAs, like these are much smaller than the FPGAs, for example, that Atlas and CMS have to run on, that we really have to have very low latency for this. Okay, so then this comes to basically simulating how this algorithm would run on an actual FPGA. So just as a reminder, I show again here this like sketch of the front end board that's sat right on top of the detector, and we have these FPGAs there. The nominal type that will be used, is from a company called Microchip, but the reason why they are interesting is because this company, they produce the only commercially available radiation hard FPGAs. So we're kind of forced to use these FPGAs, and as I say, they have to be fairly small, because on the front end, they cannot have high power consumption. Okay, this is a little bit of a technical aside, but in order to take a model that you would have trained in your favorite package, normally like in our case, Keras or QKeras with the quantization aware training, it's non-trivial to then kind of implement that into an FPGA. This isn't a CPU or a GPU. An FPGA is something which like really you just configure the bitwise logic in one go, so you can't just kind of put it straight into an FPGA. And for that purpose, there is something called HLS4ML, which is a community-wide software in HEP, which essentially takes pre-trained models in Python or the weights in Python, and then allows you to put them onto different FPGA backends, where the different backends essentially correspond to the different manufacturers of FPGAs. So for part of this project, what we've also done is taken HLS4ML and extended the backends that are available on it to also support the type of HLS syntax that is used by this company, Microchip. And there's just a pull request there. This is probably only interesting to you if you know already about HLS4ML, but I just advertise it here. Okay. So how fast and how small? So this is a table from a draft of paper we're currently writing on this. So this is essentially the numbers we get if we simulate this for the requirements of this small FPGA. So the clock frequency that we expect on this board is 160 megahertz. So that corresponds to about around 6 nanoseconds for each clock cycle. The latency, so this is always expressed in terms of clock cycles on the FPGA. So how many clock cycles did it take for you to run your algorithm? And for this very small 32-to-2 algorithm, we can do it in 4 clock cycles. So that corresponds to 25 nanoseconds, which is more or less, which is very good. Now, one important point is that, as I said, this has got to be small for 2 reasons. Firstly, the smaller it is, if it's really small, then you basically can parameterize this whole thing just in your lookup tables, and these are more radiation safe. But also, if it's really small, it means that nobody's going to be bothered by the fact that you're running your algorithm there, because these FPGAs have to do other stuff as well, so we want to show that we can do this without using a large proportion of the resources. Our mandate was that we had to use less than 50% of the resources on the FPGA, and as you can see, because that's what would be expected by classical algorithm, I should say, you can see in this case that actually what we get is a lot less than that, and so this should fit comfortably onto these FPGAs. All right. So, okay, I have 3 minutes left. Okay. So, interim summary. We've kind of demonstrated for the first time that you can have this, like, essentially an end-to-end case of having radiation-hard, low-latency machine learning on these really small FPGAs, and we achieved this really low latency, which is, this kind of latency was previously only achieved really with ASICs. It's not that impressive in the sense that the reason why it's so fast is because we can do this task with such a small model, but still. a few points on what we want to do kind of moving forward. So far, we've taken these, very small models, and we've done the case where we run this on just a single pulse shape, which is all well and good. But ideally, I mean, you could probably be a bit more cleverer. A bit more clever, can't say that word, but yeah, the irony. But so, yeah, here you have a single pulse shape. That's what we've done so far. But actually, on these FPGAs, you have 8 pulses coming into one board. So one would assume that if you did a simultaneous compression, you could probably get a better compression rate. Because, for example, you might be able to immediately recognize from some of the correlations between the pulse shapes that this is, for whatever reason, not an interesting thing to dedicate a lot of bandwidth to because, I don't know, it's an out-of-time pulse, it's got background, whatever. In order to be able to do this, though, it means that you no longer, ideally, you would no longer use this very simple MSE loss where you just kind of compare the input data and output data. Ideally, you would use what we're terming like a physics-informed loss. This is really where you would take your compression algorithm, then run it through the full chain, reconstruct your final energy, and then use that final constructed energy to then inform the loss of the encoder at the very start. So that's what we're currently working on. This is a bit more complex because, it requires really doing the full reconstruction chain. So this plot I showed before, but this is just essentially explaining it in a bit more detail. This comes from this preliminary study where we're running a graphical neural network to then perform the clustering between all these different pulse shapes to then get the final reconstructed energy, and then, kind of using that to inform the loss. But this is still ongoing, and it's, at the moment, not so clear if we can get this to work well enough in a small enough space to run these FPGAs. This is still, work in progress. Another thing we want to look at is whether or not we can do more with this latent representation, and particularly whether or not it can be used for anomaly detection, not so much in a physics sense, but in a kind of detecting a bit of a spicy pulse sense. So you have cases, if you have very high occupancy, which is what we expect with this upgrade, you can often have cases where you have, for one channel and one bunch crossing, not just one particle hitting that channel, but 2 particles. This is kind of a very obvious by eye case where you can kind of see there's a double peak structure. And in that case, what can happen is that what you then extract as your timestamp can then potentially be biased. So you may want to then flag that as a potentially biased timestamp reading. And here you see kind of, so this is the original pulse shape in blue. Then you see this orange one, which is just the downsample to the 32 numbers that are put out from the ADC, from the ASICs. And then this is what you get with the reconstructed pulse shape from this really simple 32 algorithm. Unsurprisingly, we completely missed the second peak, and we're not going to try to have a model that captures that. But the question is whether or not the fact that you would expect a worse MSE, whether or not you can see some correlation between your latent space and kind of having these more poorly reconstructed pulse shapes. But this is still this is what we're currently starting to look at, but we haven't really made much progress so far. And then finally, we currently have a summer student looking at whether or not, in addition to doing quantization-aware training of your neural network, if you can also try to do a training of your neural network where you also try to make the structure of the neural network more robust against random flips in your bits, essentially. So in the case that, you do have radiation higher than would be acceptable, instead of having to do what we call triple redundancy, which is then having the same algorithm 3 times and taking a majority vote, if you can just have a neural network which is slightly larger but more robust against these flips. Okay, and then finally, I just wanted to highlight other places where kind of machine learning can be used, specifically still on the eCal. So there's also work going on in France and in Syracuse, looking a bit more intently if you can do ML-based clustering, which we're also looking at, but we're looking at more for a physics-informed loss. But if you can actually do this clustering on the back-end electronic boards, which are essentially these TEL 400 things I label here. So these are now kind of radiation safe. They're behind a big lead wall, but they're still FPGAs. Or whether or not we should do them on GPUs. And this is kind of an interesting question because for sure you'll be able to get better performance if you run these ML algorithms on GPUs. But then, of course, you cost more throughput. It costs more money to ship the data up there in the first place. So, the question is it worth having a worse performance by running them on FPGAs beforehand? Unclear, but this is, another example of work that's going on at the moment. So okay, yeah, that brings me to my summary. So essentially, the challenges that we have at LHCb Upgrade 2 really are unique to all of LHC. We really have the highest data rates, or will have the highest data rates when we start taking data. And we can't just throw away events because our events all look the same. So we have to do compression as opposed to like filtering. And this compression, given the high rates, really has to happen right on the front end electronics boards, which are radiation hard. And so this project is just demonstrated the first end-to-end solution of doing this low latency radiation hard machine learning. That's it. Thanks.
Thank you very much. Questions?
Can I just ask why different parts of the FPGA are differently radiation hard? Is it just geometrically they're in a different place?
Yeah, so basically, as I understand it, and I'm not an electronics engineer, but basically, if you have, so things which are closer to the logic, so like these lookup tables, as I understand it, as it's explained to me, basically are then like safer and in a more radiation hard part, like physically. So it's not all the same level of radiation hardness, and there's some bits which are like just better protected, which is anything where you want to store something like permanently. So like the weights, for example. So you want it small enough so the weights can be in these, just stored in these like lookup tables. Whereas if it's in something like the RAM, then that's normally more for something which is like transient, and if that then flips, it's less bad because then it's not the whole weights itself. But yeah, they just apparently don't have the same level of radiation hardness across the whole chip. Yeah.
Hi, thanks for the talk. What's the procedure you have to go through for your algorithm to actually get onto the FPGA on the detector? Is there just a lot of steps that you have to convince people that it's good enough? Yeah,
that's a good question. So this is why we have to start with these things, even though we're taking data in like 7 years' time, like so early. So right now, we have only like simulated it. And at the moment, we are working with the people who develop the actual boards to run it on their boards to then show that the simulation of the FPGA response is also correct, and that then, it works out in practice. And then it is then kind of showing people, like everybody else involved in the project, that like essentially you really can trust this algorithm, that it's robust. In this case, I think LHCb, because we're less people and there's less people involved, everybody's normally quite excited to get anything kind of like additional kind of help and development on this. So we're already working a lot with the people, for the eHealth Electronics to kind of get this into what we call the TDR, which is the Technical Design Report for this specific subsector by December. So hopefully it will go in there as an official TDR option. And then just beyond that of a formal procedure, I don't know, but probably just kind of showing the actual hardware that it works. And there might be a case for doing it on so we will have a halfway upgrade, if you like, in run 4, which is like 2029. And there might be some scope to kind of try and demonstrate the algorithms there as well, and a bit of a test bed before they then go into the final upgrade in 2032.
Can I ask, out of curiosity, what design principle went into deciding that you should use 10 bits? I mean, there's a trade-off where you could have said, okay, maybe if I use 8 bits, I can use not a 32, but a 48 or something instead.
So the 32 is essentially the quickest rate at which the ADC can sample. So when you have an analog digital converter, like there's a limit to like how quickly it can sample. Basically, and that is the highest amount. So they might even do less than 32 potentially, but that's the highest allowed amount. They might do like 16 instead. Why they picked 10 bits in the ASICs, I don't know. Yeah, but the 32 is set by the sampling rate of the ADC. Yeah.
Thank you.
this is a quick question. Just you mentioned that the latent layer of the autoencoder was like more than the number of parameters sampled. How could this be? Or maybe I didn't understand properly.
So again, sorry?
At one slide you were mentioning that the latent layer of the autoencoder was you were getting higher number of dimensions than the number of space that you sampled to train it.
Which slide?
Yeah. This was like early in the talk.
Yeah.
Okay. Okay, maybe I misunderstood.
Okay, yeah,
okay,
so it's 2, it's 32, then went down to 2, so it's, yeah.
All right. I do not see any further questions, so let's thank Eluned again.
Thank you.